Hello, everyone, and welcome to today's webinar. I'm Shannon Butcher with PSERC. Thanks for joining us. Today we have Anamika Dubey from Washington State University, and she's going to be presenting Weather Grid Impact Model, Gas-Fired Generators Under Extreme Winter Weather. If you have a question, please submit it to the Q&A box at the bottom of your Zoom screen. Anamika, please begin when you're ready.
Thank you for the introduction. You can hear me fine, right? Great. All right. So thank you first to PSERC for inviting me to talk and give this presentation. So today's talk is about developing weather grid impact models, specifically for gas-fired generators under extreme winter weather conditions. This is a part of the research that my group has been involved with, funded by NSF SCI Award. And what I'm going to talk about today is some of the recent results and some of the works that we have done around this particular topic area. So before I start about this specific problem, one of the things that we have been broadly focusing on is about these extreme weather events and their impacts on the grid infrastructure and how they can cause large-scale outages and what kind of economic losses can incur from there. We all are aware of these billion-dollar or now even billion-dollar disasters that have been happening and has been happening at a faster rate in the past decade or so. This slide kind of shows a glimpse of those 27 separate billion-dollar weather-related disasters that happened in 2022, and the graph on the right side shows you the events that happened over from 1980s to 2025 related to freeze and winter storm. So in this particular talk, we are going to focus on winter weather and specifically talk about these models, some of these models that we have developed for extreme winter weather event. But broadly, the goal here is to figure out how can we how to know or how to predict what the impact of a given extreme weather event is going to be on the power grid components and overall on the outages that we might see and help us prepare better before that event actually does manifest. So really the research is about developing these weather grid impact model, which are basically, in my opinion, one of the gaps in the literature on how do we develop the predictive capability of estimating how a given weather impact is going to affect grid components and overall grid infrastructure and result in potential outages. So within that context, we are going to talk about one specific kind of weather event. In this particular case, these are extreme winter weather conditions, which can be categorized as winter storm or freeze events. And our question here is that what are the components that do get power grid components that do get impacted by these events, and which of these components are most critical towards predicting the outages and preparing the system better for an upcoming event? And how do we model them? How do we develop those predictive models? What are the challenges that we have faced so far in terms of developing those models, and some of our results and analysis. So very briefly, these are some of the past winter storms that this slide is showing. If you can see my cursor, hopefully. So this top figure is basically the average temperature departure from 30-year normal for the storm Uri in February 2021. And you can see that these blue shaded regions are basically temperature departure of as high as -25. So really this is a extreme. The second one is for winter storm Elliott, which is from December 2022. And again, significant departure from the 30-year normal temperature that can be seen here. And both winter storm led to exceptionally low temperature, basically. That's what the slides are showing. And they resulted in failure for different power plants. This particular graph shows generation failure by fuel type during the selected 5 extreme winter events that are shown here in the past decade. And this graph basically shows you different generation types. So this gray one is for the gas generation, the black is coal, the green is wind, and the blue is other. And basically, as you can see from this particular plot, the most sensitive generator type, as you can see here, are the gas generator during these winter storms. And hence, we focused our study on modeling these weather grid impact model for the gas generators. You can also see what is the percentage installed capacity, total percentage of installed capacity that actually got outaged or derated during these particular events. And that significant percentage, around 50 to 60% of those generators were impacted by the events. So that's one of the reasons why we focused on gas-fired generators for modeling the impact of these winter storms. Then this slide further talks a little bit more about our motivation for focusing on gas-fired generator. Once again, this is a past storm. It's summarizing basically what happened during these specific storms in terms of what was the event area, what was the deviation from the average daily temperature. And as you can see, that was significant deviation in these temperature ranges, as you can observe. And the more the deviation, the higher the unavailable generation capacity, so higher the impact, of course. And then it's also talking about, unavailable generation due to cold weather event, and then peak magnitude of the rolling blackouts that were seen because of this. We further digged a little bit deeper into what are these unavailable generation capacity because of these event as a percentage of different types of plants. So for these three storms, 2014, 2021, and 2022, this particular table is summarizing the percentage of total outage or derates during the past major storm for different fuel type. And you can see that gas generators were actually most impacted. After that, there was coal, and the rest of the generator did see some impact. For example, here in 2021 Uri, we did see some impact for the wind generator types as well. But primarily, as you can see, that it's actually gas-fired generator that do consistently get more affected because of these storms. So once again, we focused on gas generators. Before we jump into some of the modeling, details, I did wanted to highlight this interdependency between the gas and electric grid and what are different components that we need to model to truly understand how the overall, infrastructure gets impacted because of an extreme winter condition. So one aspect of course, this extreme winter event is that your gas-fired generator gets outaged and derated. But what are the different reasons for which they actually get derated, and that leads to outage problem? So this particular figure kind of summarizes some of the interdependencies between the two infrastructures that we have, but primarily focusing on what are the different equipment types and how they impact the working of different infrastructure. So here, the blue boxes are showing the gas infrastructure, and the green ones are electric infrastructure. As you can see, customer can be consuming gas or electric depending upon what kind of space heating they have, what kind of consumption they have at their end. One point to notice here is that with decarbonization, we are moving more and more electricity uses for the space heating. So that again creates further interdependency between gas and electric infrastructures. And in the past decade or so, we have significantly increased our dependence on natural gas for electricity generation as well. So during extreme winter event, these are some of the interdependencies that have been observed. For example, there could be a wellhead freeze where the gas production, gathering, and processing happens. Because of this wellhead freeze, there might be fuel shortage, which leads to this, pipelines, the gas pipelines and compressor can have fuel shortage again and pressure drop, which eventually leads to electric power plant generation capacity derated or even outaged in the case that there is no fuel supply going on. Similarly, there are storage for the fuel reserve. Again, there could be fuel shortage in the process as you get to the extreme winter condition. And then again, it can create some problems for the electric power generation plants specifically. The fuel shortage could also affect the local gas distribution company in terms of what they deliver as a fuel to their customer. This is a different, process of analyzing what the impact of the extreme winter condition could be. Our main focus is looking into this electric power generation and how does the electricity generation gets impacted because of the extreme weather event. There are now two primary causes, I would say, for electric component to get impacted because of the winter storm, specifically the gas-fired generator in this case. One is the fuel shortage itself, and other is because of the extreme winter condition leading to freezing or any kind of equipment or mechanical failure issues because of these extreme temperatures. So we did a bit of analysis here to understand what are the different causes for these grid components to get damaged. For electric, we noticed that past storms actually show that mostly generation gets affected because of different types of freezing issues, and transmission lines, which can also get affected because of freezing issues, but a small percentage of observations were recorded here. For gas system, there are production, processing, and distribution. All of them could impacted because of the freezing issues, and that can lead to shortage of gas supply for the electric generation, which then can lead to outage and derates for the gas-fired plant. Now, in this particular study, we focused basically on weather impacts on the gas-fired generator. We then did not model the impact of the fuel supply shortage. That interdependency is something we are still incorporating. But one of the main things I want to talk about here is that there are two factors, and we are focusing on specifically how weather directly impacts the power plants here, and not indirectly in sense of creating that fuel shortage. Okay, so with that introduction, briefly, let's talk about why did we again focus on generator and not anything else. These are again two storms, the recent ones. This is Winter Storm Uri, and this one is summarizing basically the total megawatt loss of incremental unplanned generator outages or derates or startup failure caused by the total event area. So you can see here most of the challenges, at least for this storm, were coming from the freezing issues, and that led to a majority of outages. There were mechanical and electrical issues as well. And there were fuel issues, which contributed to 22% of the derates and outage or the startup failures for the generators. We are in the weather-related impact. We are primarily focusing on these freezing issues and probably focusing on mechanical and electrical issues if the data is able to capture it. We're not focusing on this fuel issue and this part of the analysis. We believe that this needs to be separately modeled as a different cost problem. Similarly, if you observe Winter Storm Elliott, it has a slightly different kind of markup in terms of the freeze issues versus the different fuel issues that were observed. But still, you can see that there are different equipment and contained challenges within the power plant generator itself, which is what we are trying to model as an impact of the weather condition. Okay, with that introduction, what I really wanted to get to is that we are focusing on winter weather. We are specifically focusing on how winter weather impacts the power grid components and specifically leads to outages. Our goal is to develop these predictive models, which can help us estimate what the impact of extreme winter weather is going to be, specifically in terms of the derates or outages for the gas-fired generators. And the reason we focused on gas-fired generator is because those were the most impacted by these events based on the past analysis of the past events. So these were our key research questions. What we really want to understand is and model is component level damage within the gas grid infrastructure due to extreme weather event. First question is, how do these extreme weather conditions affect the operational capacity and reliability of gas-fired generators and possibly other vulnerable component which can be impacted by these critical interdependencies. Now, in today's talk, we are going to focus on gas-fired generators. Now, to study this problem, we needed to focus on and understand what are the key factors, for example, temperature, demand, or generator type that may influence the generator performance and outage probabilities during extreme cold weather events. Then we went on to ask this question that what modeling approach actually best captures these relationships in terms of generator performance and lead to accurate and reliable prediction. And we worked on different models, and hence one question was about how to compare and how to understand the predictive capability of these models and say something about their accuracy, uncertainty, and basically in summary, what are they providing us reliable results or not? And finally, we really want to delve into how these findings could be used to inform grid operator, planner, and policymaker to enhance grid preparedness and mitigate risk during extreme weather event. And we'll talk here about some of the limitations of our model and what can help actually make these models better and more useful for the community. So with that introduction, let me briefly talk about what are some of the existing literature in this particular work. These are some of the initial work we have found. The first one is on sequential Monte Carlo simulation for weather-dependent failures. Much of the work in this particular category of work has been done for wind-based fragility models, specifically looking into how the impact of wind event as the fragility of the component level can result in damages or for some of the components, specifically, for example, plants or transmission lines, and then how does that lead to infrastructure resiliency and defining metrics for that. The second one is again on generative winterization, but looking into more of a planning problem. So it really talks about that once you have some of these winter storm severity based on outage magnitudes, how can you come up with some of these two-stage stochastic programming model for winterization? However, it doesn't include that modeling question that we are asking right now. Then there are some outage prediction models for snow and ice at the distribution level. And once again, they are weather models that are based on snow density and freezing rain, and they are not focusing on component level failure, which in our opinion is needed in this particular case to really understand and help with the preparedness in the real system. And finally, the closest work to our work is this quantifying temperature dependence of generator failure. They examine the generator failure broadly based on across different weather conditions for different temperature ranges on how the failure and repair process for different types of generator actually emerge. And they use similar data set as we are using, and also some more sophisticated data set to really validate their findings. However, one of the gaps is that they don't exclusively focus on extreme winter weather condition or extreme weather events, and we believe that that focus is needed for us to really understand the behavior during of these components during extreme winter conditions, because we believe that the process for damage or derate is different during normal versus in some of these very, very abnormal conditions. Okay, so with that introduction, I'm going to briefly talk about our study region, what we actually worked on here. We focused for this work on this northeastern US. This is the case study for our analysis, and we focused on this for two reasons. One is that this region actually experienced several cold weather events, which caused consistent stress on gas and electric power infrastructure. And the second reason was that this project was about studying the interdependency between gas and grid model broadly, and we had a joint gas electric model developed by our collaborators, which was for this project, which was available for the system. So that also basically helped us facilitate the study for future in order to understand these interdependencies, specifically during winter condition. And then again, our model contains these 8 states, which are highlighted in green here. And the reason to really highlight and tell you about the study region is because we actually use the real data and real outage data from these regions to develop our models. So what did we use to do the model development? So again, this work is based on real world data. We have used GADS dataset for all of our analysis. GADS dataset is generating availability data system by NERC. It maintains a complete operating scenario on more than 8,000 generating units, representing over 90% of installed generation capacity in United States and Canada. And as of January 2013, GADS made it mandatory for industry program for conventional generating units of 20 megawatt or larger to report the incidences. It includes various information, including location in terms of state and NERC region, type of prime mover and fuel that is used for the generator, and outage and specifically outage and derating event information by generator unit number, start and date time, event cost, type of outages, whether it was planned, unplanned, and the percentage of net available capacity during the event period. So this provides a complete set of data for us to develop these general models. Again, I would say because GADS do anonymize the generator model data, so we don't know exact location of these generators, but we can develop some of these generic models using this data set to understand and to represent the outage process for these outage and derate process for these generators, specifically gas-fired generators, using the past 10 years of reported data. So in GADS data provided by the outage and derating scenarios are classified based on outage as when net available capacity is 0, and derates when net available capacity is in between 0 to 1. We do separate these two processes out, and you will see why we do that. One of the reasons is that we did see that there are two processes happening for generator outage and derates, and to appropriately model that, we needed to make this separation clear. And for each outage and derating event, they do provide a cause code for the event. So that also help us basically select the data set specifically for the winter events that we are concerned here in this particular work. So these cause codes, for example, could be storm, could be freezing, could be fuel supply shortage. So there are proper cause codes which are provided, which help us basically screen to the data set and use it for our analysis for appropriate, labels of the data for the models. Okay, so that's on the GADS data. This is what we have. First thing we did was we analyzed this GADS data for these 8 states, and basically figured out what were the number of events that were happening each month for past 10 years. So we took data from 2013 to 2022, extracted the data for these past these 8 states, selected only gas-fired generators in this particular case. For the cost codes of, winter storm and freeze, we basically did this analysis to find out, which month were these storms were observed, to really be selective about our study for the data set and modeling process in the next step. So for each event data, GADS does provide an event type. And for this study, we only looked into unplanned and forced outages or derating event and startup failure events. We did not include any planned outage and maintenance outage or reserve shutdown because of obvious reason. We are trying to really understand the impact of weather events on the grid component. We did also further down select the data to only winter months, focus on December, January, and February. You can see that there are some events in March, but we have ignored them for now. They do not contribute a lot to our study, but we are looking into how to really incorporate them as we expand our study a bit more. And again, we only select gas-fired power plants for this study. So now getting a little bit in more details about the cost codes and what we are using. So the GADS data has all sorts of events, categorized based on all sorts of, derate and outage events, and a cost code for those events to be happening. And there are a large number of cost codes, but one of the ones that were of interest to us, specifically for the extreme winter condition, are listed here. So the first one is a sea storm. A storm is basically, they categorize it as a cost code for any storm, including ice, snow, that might be happening. Now, this could be other storms as well, but since we are down selecting for winter weather only, it basically leads to those winter storms cases for our case. Then there are other cost code, which is fuel supply. We noticed that this fuel supply could be an important one for us to study for the gas-fired generator. So we did create a second data set for us, which includes all the data for a storm as well as the fuel supply shortage. And that basically made a little bit larger data set, a little bit larger event data set for us to do the analysis. And the third one is then some of the equipment failure events. So these equipment failure has a large number of sub-cost codes. So for example, fuel piping or valve, feed water pump, feed water valves, which are basically freezing, or feed water piping downstream are freezing. So there are a large number of cost codes which are captured within this equipment, and we took them with the ones that are associated with freezing tagline or anything that has to indicate with the impact of any winter weather cause. And we added that to our data set. So now we actually expanded our data set to also include those events which corresponded to anything related to equipment freeze or equipment failure because of winter weather. But then again, there were some challenges with the labeling of this data, and you will see what happens. So our goal was here to look into these three data sets and figure out which data set makes more sense in terms of the model that we are training for its, in terms of its predictive capability, and we'll talk a bit more about it. But just for now, these are the three variations of data sets that we have used in our model. So the next one just talks a little bit more about what these datasets actually constitute. So we, the first dataset, which only queries for the storm event, again for those 8 states and for the month of January, February, and December, and specifically for gas-fired generator. This resulted in a total event, 131 total event in the past 10 years of GADS data. Total outage events were 54, derate events were 77. So there is a a very close kind of split between the outage and derate events. The second one was a storm plus fuel. So you can see that this data set expanded our data set slightly from 131 events to close to 457 events. And out of those 457 events, 181 were outage events and 276 were derate events. And then when we expanded this data set further to include equipment failure because of freeze and other cost codes, that led to a total event of 614 total events. Outage events were around 267 and derating events were around 347. So you can see that there is a very, kind of, how do I say, model separation here in terms of outage process and the derate process. And we need to find some statistical model that can capture this kind of, semi-continuous data. So we'll talk a bit more about that in the next slides, but this basically just summarizes the extent of our data set that was used to train these models. Okay, so then the next thing is for the regressors. So we are basically training these models to understand the impact of extreme winter weather event. One of the obvious regressor for the model was the temperature, that how much the temperature was, ambient temperature was in that region. And we use basically NOAA's integrated surface database to collect these temperature data sets. So what you are seeing here on the top figure, these are all the weather stations which are in these 8 states, which are our study region. And then the triangles that you are seeing are basically all the gas-fired power plants location in the system. Now, the GADS data does not provide us the location or exact location of any of the power plants in the dataset. That's anonymized. So we do not know which power plant actually got outaged. What we do know is that where these power plants are spread across these 8 states, and we do know that where these different weather substations are spread across these 8 states. So one of the things for us to do, again, we are making assumptions in these models because we don't know exact location of weather stations and the power plant generators which got outage. So we make some assumptions. So here, one of the assumption for us was to, for the temperature data, we needed to select one temperature corresponding to each event. And we selected the minimum temperature that was observed in that particular state for that particular event, for that particular, power plant or generator where we are developing this model. Now, there are some weather stations which are not at all close to any of the gas-fired generated plants. So that was biasing our results a little bit. So the first thing we did was we down selected these weather stations, and we only kept the weather stations which are nearest to these gas-fired generators in the region of our study. And that reduced our number of weather stations. And then when we observed one particular event in the GADS data, we basically, for that particular event, we selected the minimum temperature out of all these weather stations. They were recorded at that particular hour as a regressor for our model. So some assumptions here, since we don't know at that particular event which gas-fired generator was outage, we basically make an assumption that it could be any of them in this particular state. The second assumption is that since we don't know which gas-fired plant got outage, we don't know which weather station to really map to this. So we basically, again, assume the minimum temperature that the region might be seeing could be a good enough regressor for us to work with. So that's first assumption. So temperature is our one of the regressor. The second regressor that we found to be successful in terms of having some prediction capability here was demand data or total electricity demand. And we captured this total electricity demand based on the hourly demand data for the entire, ISO New England and NYISO region reported for those particular event duration. Now, we don't have, again, exact demand data for any of those events whenever they were happening. So we made an assumption here again that because of an event, if the demand was a cause, then there might be an overall increase in the demand in the entire region. And if we just sample that hourly demand from this region, that might be a regressor enough to work with. There is, of course, a scope for improvement, but we need better data to really work with that. So basically what we did, we took the, because of our state span across New York and ISO New England states, we took basically ISO New England's hourly demand data for the entire duration. And we basically used for that particular hour, normalized the data and used that as a regressor for our problem. Similarly, for New York State, we use the data from NYISO. So that's basically what our demand data is coming from. So we use two regressors, basically in summary. One is temperature, another is demand. We also tried to use duration as a regressor, which is the duration of the event. However, it did not show a lot of predictive capability in terms of really representing anything for the observations. So we discarded that. So in summary, this is how our algorithm or the method work. We basically use NOAA's data, E-grid data, which is the gas-fired plant location and the weather station location to filter out the weather station that are nearest to the gas-fired power plant. And then we compute US state-wise hourly average minimum temperature for the period of 2013 to 2022. We use NERC GADS data for generator outage and derating event and use this 10 years data for selected cause codes, as we mentioned before, for the winter months, specifically for gas-fired generator and for these 8 states. And then we use demand data from the ISO New England and NYISO's, demand, basically hourly megawatt demand available, normalized it by dividing by the maximum demand. And maximum demand for each event duration is basically taken as a merged data set here. And then our models are basically trained across these data sets. Now, one important point to observe here is that our analysis basically predicts a generator derater outage, given that an extreme winter weather is observed. So basically, once you know that an extreme winter weather is going to be observed, which is defined in terms of temperature being less than 0 degrees Celsius during the event, and this is flagged as an event, then we can actually predict what are the outage and derates for our gas-fired generator going to be as a function of selected covariates, which in our case is temperature, and the total demand for the region. Now, let's talk a bit about model itself. What does the model look like? So once again, it's a regression model. We talked briefly about it when we were introducing the data set for the event and outage. So if you remember this correctly, it is a semi-continuous data. A large, close to 50% of the 40 to 50% of the observations are outage, which means that zero value. And close to other 50% of observations are basically non-outage. So it is a continuous derate value, right? So it's a semi-continuous model. We needed some model that can capture this semi-continuous part of our observation. So we chose a two-part model to estimate the generator's net available capacity. This two-part model is actually suitable for semi-continuous data. This is how the two-part model looks like. The first part is a Bayesian logistic regression, which basically predicts the probability of outage given an extreme weather event is observed. So it simply predicts what is the probability of observing an outage as a function of the regressor, and given that an extreme weather event is observed. The second part is a linear regression model, which estimates the generator's derates net available capacity in case a non-outage or a derating scenario happens. So the first part does a logistic regression, which gives the probability of outage. And second part basically says that if the outage didn't happen, then what is the estimated generator derate, derated net available capacity going to be, again, as a function of our regressor. And the final output is basically combined outcome from both of these regression models. And really, that just tells us that for a given temperature, what is the predicted derating that we are going to see. Now, these are all Bayesian models, so we are not just predicting the value, but we are also predicting uncertainty bounds around it. And that uncertainty bound help us understand how sure we are of our prediction. And that helps us understand, in terms of making decisions for the possible unfolding scenario. So both this first part and second part are Bayesian models, which means that they also predict the uncertainty bounds for the predictions that we are doing. Now, very briefly, we are basically, these are regression models. The regressors that we are using are listed here. First, we are going to show you the regression model with just the temperature as regressor, then demand as a regressor, and then both temperature and demand as a regressor for this model. And this particular picture kind of summarizes a little bit in more detail on how our models are working. So if you look here, this Bayesian logistic model, again, takes all the input that we have from the data set to predict probability of generator being outaged. And then Bayesian regression model basically predicts that if the generator is not outaged, what is going to be the derated value or derated capacity. And the outcome is the combination of these two-part model. So mathematically, this is how we describe these models. This is the Bayesian logistic model, which basically is predicting probability of P generator to be greater than 0 given X, where X are our regressors. And in this case, our regressor vector could be temperature and demand, as we mentioned before, or both temperature and demand. And that basically is modeled as a logit function here, which is represented here, that gives you basically a probability of going to 0 or going to 1, which means outage or non-outage based on this particular prediction. Now, the part 2 model is a Bayesian linear regression model that basically does this prediction. It says that if the events have basically 0 less than PG less than 1, which means that it's a derating event, then estimate what the expected value of derated generator is going to be, given the PG is greater than 0 and the regressors on which you're conditioning. And this is a linear regression model that we have here for this particular derate event. And once again, basically the X are our regressor, and these are the same temperature demand and temperature plus demand. And gamma here is basically the parameter vector, where gamma 0 represents the intercept of the linear regression. Gamma T and gamma D are corresponding vector parameters for temperature and demand regressors. So these are basically slopes. And Epsilon here is again normally distributed error term, which basically is modeling to some extent the uncertainty around our estimation process. And finally, the final outcome comes from the law of total expectation. So the final outcome basically asks this question, that what is the expected P generation given X, which basically is the sum of these two probabilities that says that it's the probability of generator being PG being more than 0 given X, multiplied by the expected probability of expected value of the P generation, which is the derated value, given that PG is actually more than 0 and comma X, which is basically condition non-regressor. And there will be one more term here in the total expectation that basically will be about that probability that PG is actually 0, but that gets cancelled out because in that particular case, the expected value of P generation is 0, so that particular term vanishes. So overall, what we need to do to really do this prediction is learn this logistic regression model, then learn this linear regression model on derating events, and then calculate the final outcome based on a combination of these two models that gives us the predictive model, which basically estimate the mean value of the prediction as well as the uncertainty bounds around it. So let's move on to some results, and then we will get to questions. So these are the models that we have worked on. So we have in total developed 9 models. All these 9 models are these 2-part Bayesian regression models. We have 3 storm cause codes used for data selection. So data set selection include just the storm cause code, that is storm plus fuel supply, and then storm plus fuel supply plus equipment. Very briefly, these are basically helping us down select the GADS data for the events which are specific to the winter weather conditions. So for example, a storm is just saying that whatever happened because of winter storm, and a storm plus fuel is basically saying that whatever happened because of a storm plus the fuel supply shortage. And then storm plus fuel plus equipment is whatever happened because of a storm plus fuel supply shortage plus equipment failure that might have been seen during those winter months. Then we have 3 regressors, which are basically temperature, total demand, and then temperature plus demand. And these are basically, again, what we have noticed before. The temperature is the minimum temperature based on weather station. Total demand is the normalized demand based on the ISO regions, and then temperature plus demand basically combine these two as a regressor and does these two model learning based on both regressors. So these numbers will be important as we discuss some of the results. So I just wanted to emphasize this a little bit more. So with just temperature as regressor, we have model 1, 2, and 3. Model 1 is only using a storm cause code. Model 2 is using both storm plus fuel, and model 3 is using a storm fuel plus equipment. Then the second set of models, 4, 5, and 6, only use demand as a cause code. Only use demand as a regressor, and again, the 3 cause codes that we have. And the final one here is both temperature plus demand, which are 7, 8, and 9, and then again these models. So basically, we are fitting these Bayesian 2-part model for all of them, and let me show you some results. So the first one, this slide, is about these 9 models, specifically for model 1, model 2, and model 3. And again, model 1, model 2, and model 3 are basically based on the data set selection. So this is model 1 is only storm, model 2 is a storm plus fuel, and model 3 is a storm plus fuel plus equipment. And then this is only based on temperature as a regressor. So as you see with any of these plot, we have temperature as regressor here, and we are estimating or predicting the probability of outage for these generators. So the first one is it's a 2-part model. So the first is basically the part 1, which is the logistic regression model. This model is basically telling us that if the temperature is minus 25 degrees Celsius, then the probability of outage for this particular generator is going to be somewhere around 0.45 with an uncertainty bound that goes from 0.25 to 0.6. And this uncertainty bound is basically is 95 confidence interval. So we are 95% kind of confident that we will lie somewhere here. So the point again is that, the larger this uncertainty bound is, the more we are going to be uncertain about our estimates. So it's in our best interest to really, contain it. What really contains it is adding some more data set does help contain it, but it might actually create problems with the prediction ability. So for example, if you go to model 2, where we have more data set now, storm plus fuel supply, you do start to see that uncertainty bound actually start to get compressed a bit. But then when we do a little bit more analysis on these models in terms of their statistical test to understand the predictive ability of these models, we see that this has a lower predictive ability compared to this particular model. Then model 3 adds more data, and that leads to even further, decrease in the uncertainty bounds around it. But again, it gets a little bit more flatter as a curve, and as we do a little bit more analysis in terms of figuring out how good these models are, we found that model 3 is not that great. So it really is a trade-off, but I think adding more data and more specific data can actually help a lot in improving these models. The second one is on expected value of P generation, given that it was actually a D-rate condition. So this one it's a linear model. So for a given temperature, it basically is telling me how much D-rate will happen if in fact D-rate happened, right? So condition on the fact that D-rate happened, at minus 25 degrees Celsius, you are going to see a D rate of around 0.7. It is a very small slope. So we notice that it's really not doing that good of a job in terms of modeling the D rates in this particular case. And that's why we notice that maybe some other regressor might be more useful in terms of really predicting the D rate capability. We'll talk a bit more about it. And then model 2 and model 3 are showing you the similar things. You have more data now. These red data points are showing you the data points, and we are trying to model them with the linear regression for the D rate condition. Finally, PG hat/X, this one is the actual predicted value of the based on the combined outcome of these two models. And we'll talk about how to create it, but basically this is showing you what the outcome of these two models in the combined sense will be. So essentially, this is what will be useful for us in terms of preparedness. So if you have, let's say, minus 25 degree Celsius temperature expected, then it's telling you the net available capacity is going to be somewhere around 0.3 with uncertainty of ranging from 0.1 to 0.5. Per unit. So this basically gives you that bounds as well. But basically the net understanding here is that the model is able to capture the impact of temperature. It basically tells you that as the temperature decreases, there is a significant probability of generator to be operating in a derated state. As a temperature. Yes, the probability of going into derated states actually decreases, and there is a more probability of it getting outaged. However, those two combined give us some more understanding about what we might expect in the system. Now, this is the second model, which is basically this one, with only demand as regressor. Once again, based on 3 cost codes. Once again, the similar kind of logistic regression for the outage, and then the linear regression for the D-rates. So if you observe, there's not much difference in terms of the logistic regression. It does do what it's supposed to do. It's basically telling you that as the demand is low, for example, here 0.5, you are going to have less probability of going to full outage, versus if the demand is high, you have more probability that generator will actually get outaged. And then again, it's showing you that if the demand is low in per unit sense, then the generator is going to be will be less derated, and if the demand is out, there is a larger value of D rate that possible for the generator. So it's the demand regressor is able to capture these events as well. The important observation was that demand event was able to capture a little bit better in terms of how the linear regression part goes, or how the D rates go. So we found it to be a good regressor in terms of estimating or predicting the part 2 of the model, and hence we combine them together in the next model. And again, this final one is a combination of these two, once again only with demand as regressor, and showing you what the net available capacity is going to be given you have a prediction of the demand for the system. So let's move on to model 7, which is now the combination of these two, temperature and demand as regressor. So we are now looking into 3D plots. One of the regressor is temperature, other regressor is normalized demand, and then the final one for model for part 1, which is logistic regression, is the probability of D rates or probability of outage, and the second one is the net available capacity if the D rate does happen. Now, model 7 is only based on a storm, and model 8, 9 are based on a storm plus fuel, and a storm plus fuel plus equipment. So core observation here is that we are able to get those patterns that we were looking for in terms of logistic and linear regression. So it says that at near freezing temperature and low demand, the generator is predicted to run at the derated capacity. With further decrease in temperature and increase in demand, the generator's ability to operate at derated capacity becomes lower, and it is likely to experience more outage. Now, in this case as well, these are all Bayesian models, so we do have uncertainty bounds around it as well. However, it's very hard to represent it in 3D, but bottom line is that that's what it's trying to do. And our next goal was to really understand which of these models are appropriate for the analysis, and I'll briefly talk about that. So model 7 is this, which gives you basically a predictive ability combined model here, and in summary, it captures what we were supposed to capture. This is model 8, where we add storm and fuel. You can see that an obvious observation from here is that it's starting to basically overestimate the capacity prediction and not fitting the data well. So one of the challenges with model 8 is that as we add this fuel supply as an additional cost code, this is not appropriately labeled only for the winter or winter event related conditions. So fuel supply shortage could be because of other reasons as well. And since we are kind of forcing this model to predict as a regressor of temperature and demand with the fuel supply data, which might not be kind of the main cause for leading to those derates or outages, it does a poor job in terms of estimating or predict or modeling that behavior. Similarly, for model 9, once we add more of an equipment failure as well, again, those equipment failure data is not specifically labeled for the winter storm kind of events. So once again, it starts through a poor prediction and start to overestimate and underestimate these results at different places, do a little bit more of a flatter prediction, and maybe not have a good enough predictive ability here. So one of the key observations from here is that having a good label data for the cause of what the reason was, and using that to train this model is very important. Otherwise, the prediction ability actually suffers. More data can help us contain uncertainty of models, but more data actually makes it really hard for us to say anything whether the model is actually useful or not. So I'm going to skip through this slide in interest of time. I do want you to give some time to ask questions. I'm very briefly going to talk about how did we understand, how did we validate these models, and why are we saying that these models are working or not working? So we use different types of statistical metrics to validate our model, and we did a stratified k-fold cross-validation for all our models. For the logistic regression model, we use a standard metrics: accuracy, precision, recall, F1 score, and area under the curve. And basically, these plots are evaluating the performance across different thresholds, wherever other metrics might be dependent on single threshold. So this AUC ROC is evaluating the model performance across different scores. And what we are seeing here is we are trying to figure out for all these 9 models how they score on these metrics for the Bayesian for the logistic regression part. And this is some of our results from accuracy, precision, all of these metrics. And the numbers that you see here basically are showing you in some sense relative performance of these models in terms of their accuracy, precision, recall, as well as basically how much representative they are in terms of their prediction ability. So let's focus on this metrics because it's based across different types of observations and multiple factors in terms of how this model is able to capture that. We noticed that model 4 and model 7 have the highest, this area under the curve, an ROC matrix. Just as a recap, model 4 is based on just demand as a regressor with only storm cause code. And model 7 is based on both temperature and demand as a regressor with storm cause code. So as you can see that all the performance metric actually suffer once you add more cause code, which basically indicates what I was saying before, that unlabeled data create a lot of poorly labeled data or incorrect data that we are using to explain the phenomena creates a lot of problems. So we should not be doing that. And the second thing that I wanted to emphasize here is that how adding regressor and which regressor are actually useful. So while that's the case, model 4 looks better in terms of this metric compared to model 7. We still have, other metrics to compare. For example, model 4 achieves perfect recall, but has a low precision, indicating it might have many false positive. So we do believe that adding temperature and demand both as regressor does help, improve model quality for logistic regression part. For other metrics and comparing across the model as well, we used a Bayesian logistic regression base factor comparison. Base factor basically is a statistical measure used to quantify the strength of evidence provided by the data in favor of one statistical model over other. So it's really comparing these models across each other. So this is a 9x9 matrix where we are comparing these models across each other. And we notice that model 7 scores highest in all of them. So once again, model 7, which is basically storm cause code and temperature and demand as a regressor, gives us the best estimation ability, prediction ability for this model based on our analysis. Then we did the same thing for linear regression model validation as well. And for linear regression, we looked into standard metrics, mean absolute error, root mean squared error, and mean log predictive density. And again, based on all of this analysis, model 7 actually comes out to be winner in terms of basically all three metrics. And hence we are saying that model 7 is probably the best for us in terms of explaining and modeling this phenomena. There's a little bit more discussion here, which I think you can read through it, but I'm going to skip through that. Basically, it's summarizing how we are comparing across these models and why we are saying one is better than other. This helps us understand which regressors are explaining the phenomena. It also helps us understand how to measure the strength of the model and say something about that, how useful these models are. Very briefly, how to use this model for a given input. So once we have these two models, the logistic model and the linear model, the way this approach works is that you provide this input, temperature and demand, for a given event that you are predicting is going to happen. You use these logistic and linear regression model to run multiple samples across this model because it's a Bayesian model. So you will also get an uncertainty bound and get multiple samples for the D-rate probability and the actual value of D-rate when D-rate in fact happens. So these two outcomes are given out, and then you use basically combined prediction by multiplying these two output based on the law of total probability, right? So you get that, and then basically you form a band of observation, and the mean and value of that it can be observed from that particular band of observation, and you can also get the uncertainty bound based on these multiple runs that are getting for these Monte Carlo samples. So very briefly, we did, for example, if you do it, use this model 7 for, let's say, -5, let's say use for -20 degrees Celsius temperature and a normalized demand of 0.9. It gives you that mean net available capacity is going to be 0.166 with an uncertain 95 confidence interval to be between 0.046 to 0.324, which means that the mean observation you can might look like this, but the uncertainty, it can vary anywhere from 0.046 to 0.324 in terms of its D-rate ability based on the uncertainty bound around the prediction window. So basically what I'm showing you is that this model then can, once trained, can be used for any future given weather phenomena to predict what the mean net available capacity is going to be and what is your uncertainty around that prediction value. So that's briefly how this model works and what it is doing. There are, these are some concluding remarks. There are some model limitations. So, despite the access to exact weather stations and current model, we do use the aggregated temperature data for each state because we don't have generator-specific location information available. Also, the cause codes that we are using, which might be because of equipment freeze-off, outages are not properly labeled in the GADS data set. So we are not using all the data set, but adding just without proper labeling create a problem with the model. So that also limits how many accurate events that happen and that can be used for modeling. So this model basically operates on a small data set, which also impacts the prediction accuracy and generalizability. So one of the things that we need to improve this model is if there is a possibility to access generator-specific locations for direct integration of localized weather data, then we can actually develop a generator-specific model and use that really to say something about how these different events might be, how these different generators, gas-fired generators might be impacted differently because of these events. And if we can have that access to that data, then this generalized model could be used in a hierarchical manner to do prediction for other specific generator-specific prediction or generator-specific model development based on that more localized and more detailed data for the past event. So basically what we are asking for is collaboration to acquire these generator-specific outage data and weather data, which can help us address the data limitation and help us also test out the prediction ability of these models with more improved data set and more localized data sets for our modeling capability. So I really, if anyone has access to that data and they are willing to have established collaboration to share it and to work with us, please reach out to me. It will be super helpful for us to really understand and test how these models could be helpful and useful in real world scenarios. So Our key takeaways: extreme winter weather significantly reduces the reliability of gas-fired generators. Our two-part weather grid impact model is able to capture the impact of these extreme weather events in terms of these temperature and demand as regressor for the net available capacity. However, our analysis can actually enhance a lot if we have well-labeled data, generator-specific outage data, as well as more detailed data for the winter weather condition that we can use to model and represent the ability and the predictive ability of these models. What we're also looking for is feedback from different stakeholders who might benefit from this particular study on what could make this more useful and in terms of actual operational decision making. This is one of our submitted work that we based on this particular research, and we are working on some more papers, and we are happy to share more details on that if you're interested. I do want to acknowledge my PhD student, Sajaduddin Muhammad. It's all his work. He has done excellent work in this particular, segment of work that we have talked about. So much thanks and a lot of, appreciation for him. I also want to acknowledge North American Electric Reliability Corporation, NERC, for providing access to GADS data. Many thanks to Marklavi and Svetlana. I do want to acknowledge funding and support from National Science Foundation. This project is funded under this particular award, and my collaborators include Chiara Loprete, who is an associate professor in Penn State, and Burshin Unsel from New York University School of Law. With that, thank you again for your time, for listening to me. Please reach out to us if you are interested in the study and want to learn more about it, and if you're interested in helping us out with some of the data sets that might help us, enhance this study. That's all. Thanks, everyone.
Thank you so much. It looks like we have some questions.
Okay. So I'm gonna screen through them. What key strategies can utilities implement to address freezing issues and distribution while improving grid resiliency during extreme weather events? So in my opinion, there could be many strategies that can be actually used, but one of them is definitely winterization of these assets. But I think we need to understand which of the assets are vulnerable to these winter events, and that requires developing some of these models to do the study. Of course, advanced preparedness study can also include better managing the resources when these events are being expected, and those are some other, I guess, both market policy and gas grid interface questions that need to be answered. This study was more about developing models which can help us evaluate what the impact is going to be. Next study will follow how we can actually mitigate them for an upcoming storm. Yeah, one state study was looked by Vermont out of a study. That's a good question. We are exploring that question as well. Our goal is to add that, of course. One of the reasons I think it was not included was the models that our collaborator had gas pipeline structure going to different states, and based on that we kind of downsampled our data. But it's our goal to expand this to, of course, the state of Vermont and work with that too. Okay, so was demand data from ISO New England and NYISO was applied across all state? Yes, so ISO New England data was used for all the ISO New England state, and NYISO was used for New York state and Pennsylvania. So we have made some assumptions here in terms of our demand data uses. So have you considered comparing the Northeast US with other regions? Yes, that's a really good question. We are working on it. Our approach to work on, sorry, I didn't complete the question. Some other regions that have similar extreme weather patterns to identify systematic vulnerability or best practices. So yes, we are indeed working on it. Our goal is to really go build this model in a hierarchical sense from these states which observe coldest of the temperature to some other states which might be observing similar kind of event, and see how these models can be explaining some of the other phenomena for other states as well. In the beginning of the study, we did this analysis to figure out how many events were observed in other places. And the reason we chose these states were we have a lot more data in these states than other states. So, and we needed that. We are very open to do this analysis for specific generators using, ISOs if they have a specific data available for these outages and for their region. I'm very happy to collaborate on that, and we are looking for data set to really test the ability of these models. So why are outage probabilities higher for higher temperature condition for any model while we are trying to observe outage for cold temperature? Okay, so I think there is something amiss here. I would say that the outage probabilities are higher when you have much lower temperature, which is in negatives -25. And as you go to zeros or some or -5 or -10, your outage probabilities reduce, but your D-rate value changes based on that. So it's really based on outage versus D-rate, and maybe we can talk a bit more about results to see that. But that observation is kind of reverse in our models. So I'm not sure if it is the orientation of 3D plot, but the change of probability more drastic in demand compared to temperature. That is true. We did observe that, it probably is the orientation. What we really did observe is that temperature is a good predictor for the outage probability, and the demand was a good predictor for us in terms of the derating capability. So what you're seeing is probably a combination of those two effects. We probably need to do a little bit better work in terms of representing those results. Okay, why do we need to filter weather station data and only select weather station that has, how does that improve accuracy of the analysis? So we do need to do that because the other weather stations might, what we noticed was they might be measuring some of the temperatures which are kind of outliers compared to what actually gas fire generators have seen and what weather conditions they observed. So the closer we can actually connect the weather data with the power plant data, the better prediction we will get. And hence we are, if we can do actually this study for generator specific analysis, that will be super helpful in seeing how the prediction ability of these models increase. So did you guys think about taking into account aging health condition of gas generators, pipelines, and transmission lines? So we haven't done that. Unfortunately, we don't have this data. If we do have it, this could be included as a regressor, and we can work on that. But again, it really depends upon how much data ability we have. Okay, so thank you for the presentation. Could you please talk about dataset availability used in the case studies? Are GADS and eGrid data open source? So GADS data, you have to reach out to NERC to get access, and it's easy to set up that access for research. eGrid data, in my opinion, is open source, but I might be wrong. My student can actually confirm that. But NOAA data was definitely open source for us. So accessing these data is not that hard. Or getting the access to this data is not that difficult. You just have to reach out to right people. Thanks for the presentation. I'm wondering why demand seems to help improve model for generator outage D-rate. Do you think demand is a proxy for severity? Yes, exactly. So severity for the weather event is stress on fuel system or other things that would physically stress the generator and cause D-rate outage. So we don't exactly know what is the cause for it, but what we do understand is that as you have more demand, it might be representing overall in the region the severity of the weather front itself, because it's actually increasing the electricity demand, and that does help us predict that what could be the stress on the grid system or maybe in the gas fuel supply system that might be causing additional D-rates. So again, it was a very data-driven observation since what we observed, and again, we are using demand data which for a region and not even for a specific generators. If we do have this data for specific generators, we might be able to do much better prediction from these models. Okay. So the next one is the data you have taken is based on 2 winter storms. What can be extension of the study? What are the limitations of using machine learning models? So the data we have used are not just from 2 winter storms. The data we have used are all the winter storms that have been observed in GADS data set for past 10 years. So and that led to, for our storm case, around 160, 170 events in the system. So really we used that to develop these models. Still a very small data set, but it was informative enough to understand how these different regressors actually affect the outage probabilities. Now, as far as machine learning models are concerned, I think these Bayesian models are very intuitive and very explainable in terms of how this process is going on. If we do have a very large amount of data set or some very specific generated data set that we can look into, there might be some ability of generalization that more advanced ML models can do. However, I do believe that understanding the basic regression patterns and basic causes for how these outages emerge, which are more, I would say, more explainable in a statistical model, is more helpful, at least in terms of providing some sort of insights even for modeling perspective or for preparedness perspective. But we will be exploring some of these advanced models as well, and we'll keep you posted how and when they are useful. Okay, so this question is not relevant to the topic, but how do we prove attendance because there is nowhere showing. Okay, I'm not sure. I'm going to move on. What would you recommend for future research related to this topic? So there is a lot of work that can be done on this topic. I think the first thing that we really need to do is understand whether these models are really useful or not. So I'm really inviting stakeholders to provide feedback, input, comments, and maybe even data set for us to work with. And that's one of the directions. The other direction is really to study how a gas grid interdependent system really might behave or predict the behavior for an upcoming event. If we can model that properly, we can really understand how the event will unfold and better prepare or figure out what could be the preparedness measure that might be needed. The third possible direction for this could be, how do we expand this study for other types of events? How do we study what are the regressors which are impacting other events, and are there better models to really capture it? What are the ways to really contain uncertainty in these models and be a little bit more sure about our models as well? So there are different aspects of it to really think about, both from regressor perspective, from cost perspective, from different storms or different weather phenomena perspective, and really how to develop these general weather grid impact models. I think it's a big gap in the literature to really figure out what the weather grid impact model are, specifically for extreme weather situations. We don't know those models for regular situations, but this needs to be systematically developed in a sense that it actually is explainable of the phenomena. At the same time, it can be absorbed by regular power system analysis packages which are used for operations and planning for the power system. So developing these models, this particular gap between weather to grid impact during extreme weather condition, I think is in general a gap here. Okay, so let's see. Can we do stability analysis for winter situation and the grid remain stable? We haven't looked into stability analysis much. I think this is basically just about what could be the available generation. And I think once you predict that available generation, if you do have a power system model, which is doing, dynamic analysis, you can use that to run it and figure out whether it's going to be stable, and maybe also plan for, proactive mitigation schemes as you take this input from our models. So I might have missed, but did demand factor also factor in natural gas demand for residential users beyond? That's a really good question. So, here we are focusing on just electricity and gas-fired generator. There's definitely an element of demand to the gas demand itself, which requires us to model gas grid together as a coordinated, interdependent system. And that's where you might see how the gas demand itself from the customer and electricity demand from the customer can play the trade-off of creating different types of vulnerabilities between these two components. So for example, because of decarbonization, we are switching these natural gas uses for space heating to electricity, and that's also causing the shift in the what customer needs during winter condition. Do they need electricity? Do they need gas? How many of them need gas, and how many of them need electricity? And what kind of mechanism exists for prioritizing these customers based on different infrastructure? So all those questions become interesting when you think about these interdependencies. We are trying to answer some of them in this particular project, but there is a lot to do here in this particular work. Okay, so then did the proposed model successfully? Yes, that's a really good question. We did it for at least some past storms, and it was able to give us good enough prediction with uncertainty bound for some of them. We are working on papers for this particular study, and we'll keep you posted on what we observed. Again, we have a lot of assumptions, so we definitely didn't do a very good job, but as I said, the main point is more data and more label data and more specific data can help us enhance these models. So in the problem, yep.
Sorry to interrupt. It looks like we've gone about 6 minutes over. Did you want to do one more question and then we'll put up our poll?
Okay. Let me see.
I think you've got Stephen Nielsen and Ian Dobson are the two next
Yes,
questions.
I can try to address these two. Those are the next ones. So in the probability graphs, why are uncertainty bounds widest towards the extreme of temperature demand range and narrower towards middle? This is basically a data artifact. We have a lot more data in the middle and a lot less data in the extreme. Since we have a lot less data in the extreme, we actually get a larger uncertainty bound. So having more data will really help solve this problem. The next one is the gas supply for the region comes from outside of the region. Should temperature where gas is produced be considered? Yes, that's a good question. We haven't been able to do a lot of work on looking into the fuel supply shortage or anything with the gas supply itself. Again, it's a data set problem. If you do have an access to some good data set that we can use to understand how gas fuel supply impact, during these events that we can use in our model, that will be super helpful. So I don't have a good answer to this question. I think it will be good to study this. However, we need appropriate data set to be able to do something about this. I think those are the questions, and I think there's few more. Probably two more. Do we want to maybe do in chat?
I will go ahead and provide you with the written questions if you
Okay.
want to answer them separately. I want to thank everybody for attending today and thank Anamika for giving this wonderful presentation. As you can see, we have launched a webinar poll. If you don't mind participating, it helps us improve our webinars. You'll find slides and a recording of this tutorial on the PSERC website as well. Our next webinar is on February 12th, and we hope to see you all there. Thank you very much.
Thank you, everyone.
Thank you.
So I can hang up, right?